This video I would like to introduce you a very nice problem regarding arithmetic number theory. Here is the following setup for all e sub n and b sub n as integers, and also n is an integer must be super equal to 1 to satisfy this following equation. So we get e sub n plus b sub n is multiplied by square root of 2, which equals 1 plus square root of 2, all is raised to the n as a power. So the main goal, we are going to prove GCD of these integers e sub n and b sub n equals 1 for all integer is super equal to 1. Okay, in order to prove this one, let's check n equals 1 first to see what's the general expression when you replace n with the number 1 here. Okay, so if n equals 1 is going to give us e sub 1 plus b sub 1 is multiplied by square root of 2, which equals 1 plus square root of 2, all is raised to the number 1 as an exponent. Okay, if you take a look at this expression, what's the relationship between these two terms and this one? So it's clearly e sub 1 equals b sub 1 equals 1 here. This one implies e sub 1 equals b sub 1, which equals number 1, because as you replace number 1 here, you get the same thing here. Okay, if I'm going to involve the GCD into these two terms, so this one immediately is telling us GCD of e sub 1 and b sub 1 equals 1. Okay, this one it's very nice here because it's going to give us a nice image how to prove the GCD of these two terms, since we get the base case e sub 1 b sub 1 equals 1. Okay, as you replace n with number 1, so this one is going to give us a nice idea. This one is forcing us to apply the induction hypothesis, since we have proven the base case. Okay, the base case is proven. Now applying the induction hypothesis here, let's suppose GCD of e sub n and b sub n equals also 1. We need to prove GCD of e sub n plus number 1 and bn plus number 1 equals 1. Okay, proof. So for all k is super equal to 1, assume that GCD of a sub k and b sub k equals 1. We need to prove a sub k plus number 1 and b sub k plus number 1 equals 1. Okay, let's take this one as a true assumption and work on it. Get this original expression, let's replace this one with k. So get a sub k plus b sub k is multiplied by square root of 2, which equals 1 plus square root of 2, all is raised to the k as a power. Okay, let's submit k to the k plus number 1. Okay, let's replace k with k plus number 1 here. So this one is going to give us a sub k plus number 1 plus b sub k plus number 1 is multiplied by square root of 2, is going to give us 1 plus square root of 2, all is raised to the k plus number 1. Okay, so we need to work on this one in order to make a nice relationship between the right and the left hand side of this equation. I'm going to distribute this one out. I get 1 plus square root of 2 factor 1 plus square root of 2, all is raised to the k. Let's replace this term with this one. Okay, so this one is going to give us a sub k plus number 1 plus b sub k plus number 1 is multiplied by square root of 2, which equals 1 plus square root of 2 factor e sub k plus b sub k is multiplied by square root of 2. Let's distribute this one out. If I'm going to do that, I get e sub k here plus square root of 2 b sub k plus the third term, which is a sub k, is multiplied by square root of 2 plus b sub k plus 2 is multiplied by b sub k plus number 2 is multiplied by b sub k. Now let's take the terms which is not including square root of 2. So we get here the following expression: e sub k plus number 1 plus b sub k plus number 1 is multiplied by square root of 2, which equals e sub k plus 2 is multiplied by b sub k plus the terms which has square root of 2, which is e sub k plus b sub k, all is multiplied by square root of 2. Okay, it's more clear. So let's replace this one with a sub k plus number 1 by matching term by term. So this one will be replaced with b sub k plus number 1. Okay, now we need to prove the GCD. So the GCD of these two terms of a sub k plus number 1 and b sub k plus number 1 is going to be replaced with these two terms, is going to be replaced with this one here, so which is GCD of a sub k plus 2b sub k, the other one which is a sub k plus b sub k. Now we'll have a nice combination linear here between these two terms of the GCD. If I'm going to subtract or add the multiple of this one on this one, the GCD is not going to be changed. Okay, let's do that. Let's put this one minus this one. Okay, so we get GCD, so I get e sub k plus 2 times b sub k minus e sub k minus b sub k. The other one is going to be the same, e sub k plus b sub k. So cancelling out this one with this one, and this one cancelling out this one down to the b sub k. So I will be left with GCD of b sub k and e sub k plus b sub k. Also, if I'm going to make some change in here, since I get b sub k here, if I'm going to do this one minus b sub k, because subtracting adding the multiple of this one, the GCD is going to be the same. Okay, so I get GCD of b sub k, which here I get e sub k plus b sub k minus b sub k. Okay, so this b sub k will be cancelled out. I will be left with GCD of b sub k and e sub k. This one is not necessary to go in order. I'm going to switch them. The GCD is going to be the same. Okay, so this one exactly equals GCD of e sub k, b sub k, which equals our assumption that we have chosen before, which equals 1, 1. What does this mean? So what we have done here, we have proven GCD of these two terms, e sub k plus number 1, b sub k plus number 1, and calculate these things all the way down. It gives us equals 1. Okay, because this one equals all these things, which is equals 1. So which means we have proven our assumption, which means therefore we found GCD of e sub k plus number 1, b sub k plus number 1 equals 1, which means GCD of these two terms, e sub n, b sub n equals 1. Okay, so I have done this problem. Thank you for watching. I will see you next video. Bye.